Welcome back to the History of Automation podcast and show. My name is Shawn Tierney, and along with my co-hosts Jeremy and Gary, we'd like to ask you, before we get into the show, if you've been enjoying these episodes and if you think we should continue it in 2026. Now, it's quite a time investment every Sunday to meet with people and to recruit people and to interview them and then to edit and upload it. And so we want to make sure that if we're doing this, that there's an audience out there who wants to hear this every couple of weeks. And so we're asking you to place your votes. You go to givesendgo.com/automation museum, and you can make a donation like $5, $10, or $20 if you'd like to see us continue in 2026. And if we get no votes, that's okay too, right? Maybe the timing isn't right for an automation museum. But if you're enjoying the interviews we're doing with some of the legends in our industry about some of the products, the creation of some of the products that we all use and love on a daily basis, well, then please consider going over to givesendgo.com/automation museum and help us raise enough funds to get this nonprofit off the ground. And either way, I want to wish you all good health and happiness. And now let's go ahead and get into this week's episode of The History of Automation. Hey, everybody. Welcome back to the History of Automation podcast. Shawn Tierney here, joined today with a special guest. But first, before I get to him, I want to welcome back our two co-hosts. Gary, thank you for coming back today and joining us again. Gary, of course, you guys know from our previous podcast, he is the author of The History of a Safer World, the true and amazing story of Triconics and Wonderware. And we've already kind of gone over in previous episodes, Triconics and Wonderware. Triconics, if you don't know, is a triple redundant PLC system. And then, of course, we have Jeremy. We've talked about his long and storied career. Jeremy had started out as working with Alan Bradley, and he's had so many roles. Jeremy, how you doing this weekend?
You know what? I am doing just fine. Thank you very much. It's appreciated to be here. I'm very appreciative of our special guest for being here with us today.
Yeah, and Chuck, like we all can't say enough how much we appreciate you taking time out of your weekend to come on the show and tell us a little bit about your career. You were in there at the beginning of a lot of this industry. And so, but before we jump into that, can you just tell us a little bit about yourself and a little bit about what you did during your career?
Well, I consider myself a automation engineer. I get off on making motors move and doing marvelous and wonderful things in the automotive business, in instrumentation, things like that. I am a techie. I am not the manager type or anything like that. I am a true techie, and I owe a lot of that to my friend and mentor, Dick Morley. Dick and I go back a long way to 1967, as a matter of fact, and I joined Bedford Associates, and I was the only software guy in the whole group. And so after Modicon, I left Modicon in 77 and broke out on my own. Went into numerical control. Did a lot of work within numerical control simply because before Modicon, there was a company called MCC, Machine Control Company. That was a Bedford Associates spinoff, and we did numerical control. This was computer numerical control, which was brand new at the time. So I had a background there. And so that company was called Encode, was very successful. I get bored easily, let's put it that way. Had to find something else. Okay, had to find something else. So what went on was Morley came back to me and said, hey, we have a problem over here. He was trying to do the company was called Functional Automation. It was a monster PC, a monster. And it didn't work. It was not accepted by the industry. But knowing Morley, as we both do, or all do, So what? We'll move on to something else. And then went to, I hate to use the term, but artificial intelligence. But this is back in the 80s. And Dick came up with an idea for a processor for parallel processing that was unique and is unique even today, even though the company did not succeed. The concept was marvelous. Picture 1,024 processors, all running independently of each other. All right. And all you got to do is program them. Okay. Sure. Okay. So
Yeah. Piece
I
of
was
cake.
there. I was there. I was making our quote artificial intelligence. I showed how to simulate an electrical grid. I showed how to save paint in a General Motors plant in the paint shop. There's all kinds of things that went on. Then that all settled down, and I retired. And that lasted all of about 3 months. And besides, there were two things. There were two things that happened. One, Morley got in touch with me. Two, my wife was getting tired of me around the house. So it was it was a great mix.
Win-win.
It was a win-win. Yeah.
Yeah.
And so out came Watchman, Pool Shaft, and what we call Blinky. Now, this is the early 2000s. Pool Shaft was a unique way of getting heat out of an electric motor. Now, we're not talking the electric motor you find in your hairdryer. We're talking about the electric motors you find in trolley cars. We're talking about electric motors you find on board huge ships, like submarines, like the USS Los Angeles class. Okay? Big motors. How do you get the heat out of those things? Because heat is the killer of electric motors. Dick came up with a unique idea. Now, as you will think about it, there's no software involved, but I was involved simply because Dick and I can bounce ideas off each other. We have a rapport that people have watched, and it's just fun. It sounds like we're arguing, but obviously not. But we're just challenging each other. So I was there from the beginning because simply I could ask the right questions. Blinky. Here's the problem. You have all these machines out on the shop floor. I don't care what you're making. Doesn't matter if it's beer or cars. Makes no difference. You as a manager want to know how's things going out there. Sure, you get your reports and you have your wonderware and all of that stuff. But, there's something about the human eye and the human brain. You look out there and you say, I wonder what, are things moving along the way they're supposed to? Well, Blinky was there to help. What that does is that we would put sensors in critical areas and learn the operation or the reactions of the sensors to various stimuli. And we would then learn which is good, which is bad. And we would flash a light. The three lights, red, green, and amber. And depending on what was going on, we'd just, flash a light. So you human could look out and just look at the light pattern and determine if things were okay. That was Blinky. Watchman. Watchman was a spin-off of Blinky. Getting back to big electric motors, big ones, railroad, trolleys, big traction motors. You want to predict when there's going to be a failure. You don't want to wait for the failure. because, obviously the motor's going to be out on the track somewhere. So we put together a whole bunch of sensors and put them on a motor and monitor them, including the position of the geographical position of the motor. In other words, we had a GPS receiver. We monitored all things, all kinds of things, magnetic fields, the temperature of the drive shaft, the outside temperature, the winding temperature. There's all kinds of things that we monitored and put together a summary, good, bad, or indifferent, And so we could predict when failures occurred. That was a great project. It was a lot of fun, too. Unfortunately, it went nowhere, simply because the guy who was funding it ran out of money and interest. So, and that's about it with Morley. Okay. Sure, there's been other things that went on in my career. I was an independent contractor. I worked with many companies in my area. I'm talking about southern New Hampshire and northern Massachusetts. And solved an awful lot of problems for them. One of the things my customers had to get used to is the fact that I will use chaos at all times to solve a problem. I'm a big believer in chaos. The parallel processor that we did, Flavors Technology, made me a convert for chaotic operating systems. So I use it, and it's proven its worth in many projects that I've generated for people. So that's about it in a nutshell.
Very cool. Ken, you say one question I was going to ask you is, when you developed the firmware for the 084, what compiler development system language did you actually employ to write that?
You got to remember the time. Let's go back. Let's get in the Wayback Machine. Okay. Let's go back. We're talking 1968, 1969, 1970. Okay. The only large-scale language was COBOL and Fortran. That's useless.
An assembler, right?
Well, there's always assembler. And so, yes, the 084 processor was written in assembly, right, by me. I was the software department, and the whole thing. Okay. Now, besides the PLC, by the way, it was called a PC at the time.
It was.
Program control. This is before politically correct. Okay. Anyway, so everything was in assembly, but also we needed two pieces of support software. We needed one, a way of getting into this magical processor that we had just designed and control it, because we had the debug software. So we needed a, quote, debugger. Okay. So I had to develop that. Plus, I'm also developing the code for the PLC. Further, once we got this marvelous, wonderful thing and we could program in ladder logic, we had to document the ladder logic. The customer wants to document his ladder logic, right? Well, it's as we now say, it's a small matter of software. All right? Absolutely. So they say, Chuck, we need another piece of software. All right. So go develop that. And I mean, guys, I'm the only one here. Okay. I have to split my head. I got to split my time. All right. I gotta handle Mike Greenberg, who's developing the processor. I gotta handle the other hardware guys plus myself, because I need debugging tools. And, I also now have to handle the future customers in their documentation. So it was quite busy.
Mm-hmm.
I was busy.
I think we should take a step back, Jeremy, and correct me if I'm wrong, or I'm wrong, Chuck, but we're talking about GM, the standard machine controller they wanted somebody to make for them. And so
Okay.
Bedford Associates, you guys are like, we'll do that. Tell us about,
Mhm.
like, let's back up
All
a
right.
little bit before we go to the firmware side.
Good. Thank you. Thank you. All right. I need direction. Okay. Because I can go anywhere. All right.
You're a software guy, of course.
Of course. Okay. Let me tell you what really happened.
The real story.
All right. It's 1967. I'm over in MCC, Machine Control Company. This is before Modicon. And so what do? We take a PDP-8F computer and we put it in an EMA box and we surround it with all of this electronics that protects it from high voltage and shock and temperature and all of that good stuff. And we do it over and over and over again. I worked on 3 projects in 2 years where we did that continually. And so I, along with a couple other guys, said, guys, this is a product. This is a real product, an industrial strength computer. Right? Now, we don't know exactly what it's going to look like. We don't know exactly how to program it, but man, there's something missing here. So let's keep an eye out for things. All right. So then Dick gets this wild idea for what it becomes the PLC, January 1st, 1968, writes the memo. And we say, oh, that's wonderful, Dick. Okay, great. You got that's nice. What? Do you have somebody to sell it to? No. Okay. All right. So then we get the word that Hydromatic is going to a show. It's in Detroit, and they're going to present a request for papers. Now, I don't know who was in the audience. I don't know the name of the person. I know it wasn't Dick, but I don't know who was in the audience. And it was an epiphany moment when the guy from Hydromatic got up there and did his presentation. This is what we need. And we said, oh, shit, this is it. Okay. Now, I mean, we don't know anybody in Hydromatic. We don't know really anybody in General Motors either. Right? Felt, okay, this is a good idea. So let's see what we can do. So Dick and somebody else, and I don't know, I can't remember who it was, got on the phone and got in touch with the author of this paper. They said, come on out. We want to talk to you. Dick goes out there and pitches it. And there's no diagrams. This is all off the cuff. We're going to promise you the moon and, anti-gravity, time travel. You know how it goes. Okay. So the guy's interested. And he says, give me a proposal. And so Dick, who has already written the memo, modifies it and makes it look pretty and all of that. And they go out and Hydromatic says, we would buy something like that. And so Dick comes back, and I distinctly remember we all gathered around in one big open room. There was a good, 10 of us, something like that. And it was an oh shit moment. Now what are we going to do? Okay. They bought it. They bought the idea and they want something. What do? We don't have anything. Okay. So that's how it really started. Okay. And okay. So we say, all right, well, we need a processor. We need our own processor. This PDP-8 thing is just, it's not working the way we want it. And that was probably the only processor that was available. I mean, you got to remember, this is before we had these things called integrated circuits. Mm-hmm. All right, integrated circuits were just coming out.
Yep.
Mm-hmm. And all they were memory chips that hold 8,000 bits. Okay. Well, that's nice, but I can't use it. There were no processors on a chip. No way. Okay. So, all right. So Mike Greenberg, myself, and Dick sat around the table and said, it's got to do this. This process. Now we're talking computers. We're not talking PLCs. We're talking computers. It's got to do this. It's got to have this. It's got to have that. It's got to have this. Oh, and we made a list. And Mike Greenberg was given the task of, okay, Mike, go design it. Oh, and by the way, you got to be able to take 10,000 volts on your input voltage. You got to. I forgot what the temperature spec was. Operating, not storage. Operating temperature. All right. Oh, and by the way, there's going to be a guy. He's going to attach his welding ground to your ground, and he's going to do welding on the very cabinet that you're mounted in. So you got a little ground problem, okay? Electrical ground problem, all right? Wow. I mean, these are nasty, nasty things.
Yeah.
So Mike, he's just sitting there saying, sure, and he's writing notes, okay? And so he comes back to me and he says, well, what kind of instruction set do you want? Now, again, this is before C and C++ and all. Everything's in assembly. And so I just gave him a list. I just went over to the PDP-8 and basically said, yeah, this is what I want. All right. But it was based on that. Okay. Yeah, this is what I want. Now make it. Okay. Well, how much memory do we need? Oh, I don't know. All right.
The important question.
Yeah. Just 40K.
Come on. Oh, and by the way, it's going to last through a power failure. Okay.
Ooh.
Oh, all right. In other words, you can't lose the operating system. You can't lose the user's program just because you turn power off.
Yep.
Okay. Minor. All right. Now, you got to remember this is 1968.
Yep.
Okay. So that's why we went core. We actually had core memory. Huh? And it worked. And Mike did just a wonderful job of on the processor, because that basic design lasted 084, 184, 384, 484. Okay, the basic design inside lasted that long. That's a long time.
That was over 10 years, isn't it?
Yeah, that's over 10 years. Okay. Oh, and then, it's got to be, we have this temperature problem. Okay. So Tom Boisvane, Tom, come on over here. All right. We got a box. We got this electronics in it. We don't know how much power it takes. We have no idea how warm it's going to get. Okay. But you, Tom, you got to get rid of that heat with no fans. Okay. Have a nice day.
Yeah.
Ron Malcolm, he was a newbie. He came in and he's Ron is a digital guy. I mean, pure digital. All right. Oh, Ron, we need a power supply. All right. And of course, power supplies are analogs. Okay. So, Oh, and it's got to have this for input voltage. It's got to be able to take spikes. You got a ground problem. You got to isolate the rest of the processor, the I/O, all of this stuff. Okay. Have a nice day. So off we went. I mean, that was it. Off we went. I was imagining code for the operating system way before Mike Greenberg was even close to making a prototype. We knew, for example, one of the problems that we knew whatever we make, we had to obviously do it in stages. And so we'll leave the memory problem, how to interface to the memory, for another day right now. Let's just get this processor running. Well, it's got to have memory because I have to load instructions into it. So where are we going to get this memory? Well, we'll use direct memory access on the PDP-8S. Great. That'll work. Right? It'll be slow, but it'll work. So, okay. Now we have a small matter of software. How do you organize it? How do you load it? Mm-hmm. And I figured out, besides doing all this, I can debug it from there too. So with a little trickery, I was able to develop that software quickly. And so all of a sudden we had memory. Of course, it wouldn't last through a power failure, but we're talking prototype. Mm-hmm. All right, so who cares? Things like that. I mean, these things just came at us all the time. What about this? What about that? What about this? And luckily, we survived it because we had heated technical discussions. Let's put it that way. Okay. So, and that took about a year and a half. 2 years, maybe. Mm-hmm. We weren't ready for a customer until late 69, early 70, somewhere in that region. Okay. And what did Dick do? He found a guy up here in Vermont.
Hey guys, I'm just breaking in here. I hope you're enjoying this week's show. I just wanted to remind you that we're asking you to vote with your wallets. If you want to see us keep giving up our Sundays to do this, we'd be happy to. We love doing it. We get some great people lined up for 2026. But we're going to need you to vote to let us know that you want us to do that. And the way you vote is you go to givesendgo.com/automation museum and you make a $5, $10, or $20 donation. If we can get up to, I think it's like $800 to actually file the paperwork for the nonprofit, we'll try to do it ourselves and save money if that's all we can raise. Then yeah, we'll keep it going in 2026. We actually have some great guests lined up for the show, but we need you to vote. We need you to vote and let us know you want us to continue doing it. And because we love doing it, but we just want to make sure we're spending our time someplace where people think it's valuable. So again, if you want to see the History of Automation podcast and show, continue to go. If you'd like to see the Automation Museum become a reality, please visit givesendgo.com/automation museum and place your vote with a $5, $10, or $20 donation. And we appreciate it. We appreciate it. And again, we'll continue to bring you this show if you think this is something valuable. In any case, I do want to wish you all good health and happiness. And now we'll return to the rest of this week's episode of the History of Automation podcast and show.
With, what was it? They're a lathe manufacturer in Springfield, Vermont. I can't remember their name. Landis?
Might be. I have a document that says who it is, but Landis makes sense.
Yeah. Well, their chief engineer, Dick, knew from, a previous life. And so Dick contacted this guy, and I can't remember his name, because he knew he was a hard ass, but a good guy. I mean, he was tough. Okay. Because he was facing the same problems with his product. So we had this we finally got the casting work done, and we got the boards built, and they were all hand kind of made with patches all over them, but they worked. The whole thing worked. And then we put it all together. We laid it down in a station wagon and drove it up to Vermont for the demo. And Dick was going to give the demo, and as they pulled it out from the back of the station wagon, they dropped it. Well, it turns out everything was okay, but you know how it goes. So they dropped it. They were able to put it on a hand truck or a forklift and bring it in, plug it in, and there weren't any sparks or anything like that. And it worked. Maybe there were 2 or 3 outputs and 2 or 3 inputs, something like that. All right. But it worked. And I think his first name was Stanley, but don't quote me on that. But because he blessed it, he said, yeah, that'll work. All right. That was our first time that we had a person from outside our group actually use it and say, I like it.
I got a question. So you developed the operating system. How did the user program it, the 084? So you did all the assembly, but they're not using assembly, right?
No, they're using ladder logic. And what we did was we decided to have another device called a programming panel. And what it was a panel in a box. It was portable all by itself, and it plugged into the 084, and it needed the processor of the 084 to run. Okay. So in other words, the programming panel was not an independent processor at all, like we would do it today. But yeah, you got to remember, processors are not cheap, and blah, blah, blah. Yeah. So the processor ran. That was just another task for the operating system that had to run the programming panel. And the user and it was all buttons. This is no CRT or no LED. It was just push buttons. And so we had the 4 nodes, and you would dial in what line number, ladder line number, and it would bring you to that and show you the configuration in the switches. And they were lit switches, and that told you what it looked like, and then you could change it to whatever you wanted, and that was it.
So you're saying 4 notes? So there were 4 instructions on the rung.
Don't think that way, because that's not right.
Well, what is it? Tell me what
were the nodes.
A node consisted of a relay contact. It looked like a relay contact. There was normally open, normally closed.
Okay.
Sound binary? All right. So it's normally open, normally closed, or it could be an OR. In other words, if you decided you wanted to have an OR function, that had to go to the left-hand rail. Remember, the logic flows from the left rail to the right rail. So as you would put in your nodes, they would be ANDed together until you got to the point where you wanted an OR function. But that OR would come back to the left-hand side of the rail. So you could not jump around a singular node with our language. You always had to come back to the left-hand rail. Okay.
Now, was one of the 4 nodes the output?
No.
So how did you?
There are 4 inputs to each line.
Okay.
All right. And then that feeds an output.
Okay.
So that goes to the right rail.
I got it.
Okay. That's why it's called ladder logic. And that's why, in my humble opinion, it was a hit right out of the box, because we didn't have to teach the electricians anything. They understood it immediately. Okay. Sure, there were tricks you could do. You could say, this is a, and I'm going to use computer terms, but we didn't use them. there was a Boolean line, okay, and it was just logic. Then you could make it into a timer. You could make it into a counter. And that was it. In the beginning, that was it. Those three functions. You had Boolean, timer, counter. Okay? Let me tell you a little funny. It wasn't funny at the time, but it is now. All right. Okay, so we're going along. We finally get the processor running. We get the OS running, and we start actually programming. The programming panel was working, and we can actually put in user programs. So we put in some user programs, and they work. And hooray, we have a party. We'll go get drunk. The whole bit. And we were big patrons of the 99 restaurant. Anyway, okay. So we say. So now we're getting a little bit more brave, all right? So we put in more. We're actually doing something. We had a ladder diagram of somebody from somewhere, and so we decided to implement it. So it took about, I don't know, 50, 60 084 lines to do that function, okay? We plug it all in, and the run light goes out. Uh-oh. You guys know what the run light is. It's the watchdog timer. Okay? The watchdog timer is an independent function, and it says, you're taking too long. Okay? I'm going to shut you down. Okay? So, we plug it all in, and boom, run light goes out. No shit. And of course, we say, well, there's a malfunction. Okay, so I go looking for this malfunction. Mike goes looking for his malfunction. Everybody's looking around at their own belly button, the whole bit. And, oh my God, the sky is falling and the whole thing. Yeah. And we come to the conclusion that we're too slow. Whoops. Whoops.
Was the watchdog timer hard set? Was it? It wasn't variable?
No. It was of our own design, too.
Okay.
Because this is before you could go get a chip.
Yeah.
Mm-hmm. Okay, you got to remember, we got to make everything.
Yep. Mm-hmm.
So, and of course, Morley would not allow us to extend that time.
Ah.
Well, and he was right. He was right. So, okay, what do? We panic. That's what we do. So Mike, myself, Ron Malcolm, and somebody else, we got together and we say, how are we going to solve this problem? So I'm of the opinion we need a hardware assist on this, because I'm saying, hey guys, you hardware guys can solve Boolean logic, faster than me. Right? That's what you guys are doing. That's how the processor works. Mm-hmm. Right? So why don't we make a new piece of hardware, and I'll feed it, and it'll give me the Boolean that I need, and everybody's happy. And of course, no, we don't have the resources. We don't have the time. I don't know how to do it. Blah, 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 blah. And so we go back and forth. And I said, guys, not unless you increase the clock time of the processor, and they're never going to do that. You guys are natural to handle Boolean. So let's you guys handle Boolean. So reluctantly, they came up with what is affectionately still known as the stunt box. Right? And it's a piece of hardware that's unique to handle Boolean. The software feeds it, gets the Boolean result, and said, thank you very much, and moves on. Okay? Ta-da, we solved the runtime problem. Right? But that was 2-3 months delay. Easy.
Wow.
Easy. Okay? Because, here's a new board we never thought of in the original design. Luckily, we had a backplane that could take it. But we had to use another backplane slot, and we had a brand new board. So we got to manufacture a brand new board. Now, we're not even there yet, but, everybody knows it's, we're going to have to build this thing. So there's the stunt box. And it's the C128. 128, sorry. C128 is the board number, is affectionately known as the stunt box. And that was the major panic in the development of the 084. That was the stumbling block. Okay. And it worked. And from then on, we still had runtime problems, but we had a different way of solving that problem. Let's see. I'll be quiet now. You got
I got one more question. I got one more question. How do I address the I/O in this original 084? I'm choosing normally open, normally closed, but how do I tell it which of those input or outputs that this normally open or closed is looking at?
Ooh, okay. It's fixed. Line number 1, the output, the Boolean output of line number 1 goes to pin number 1 on output board number 1.
Oh, really?
Mm-hmm.
So line number 1 was for that output.
It's fixed. Line number 2, the output of line number 2 goes to pin number 2 on board number 1. Line number 3 goes to pin number 3 on board number 1 until you get to 16. Internally, we're base 16.
Yep.
So you got 16 outputs on each output board. All right. And it's fixed. So if you're on line number 17 in your program, the output of that line goes to pin number 1 of board number 2.
How about the inputs? How did you choose the input?
Funny thing about that, okay, they were, the inputs were assigned, okay, so now we're talking about addressing in pin number assignments, okay? We always, in the 084, we always talked about fixed pin numbers in 4 digits. If the lead digit started with a 0, it was an output.
Okay.
If the lead digit started with a 1, it was an input. Funny thing about that. If the lead digit was a 2, it was a memorized output that held its state through power failure.
Okay.
So if you made...
Latch.
I'm sorry?
Just like a latching instruction.
That's it. They were latches. So every output had a latch. Every output had a latch. You didn't have to assign it. We gave it to you for free. Okay. So that was the 2000s. 3000, now we're going in. 3000 said that is a 16-bit digital input that is represented in BCD.
Oh.
So if you wanted a timer, for example, and you wanted to set the time, having your thumb switches out on the panel, you would take those thumb switches, the 16 bits out of that thumb switch, and bring it to that board, that input board, and it would appear in the internals as a 3000, a lead of 3000 number.
Were those the same inputs we saw in the 1000s?
Yeah.
Just in BCD? Okay.
Those are they have the same. And the board looks the same.
Yep.
Okay, because it is the same. It's just how we internally interpret it. And conversely, guess what? 4000 is BCD output. Okay, so you can drive a display, whatever you want.
Nice.
Right?
What you're describing is Modbus protocol as well.
Oh, yeah.
Right?
Guess what?
10 years later.
Yeah.
10 years later.
I know. Perfect.
But you could see that you're building it in your head. You're like, that's what Modbus is.
Yes.
Sure, because you see, just to go off a little bit on my bus, we had this customer, this very good customer of ours called General Motors. You might have heard of them. Okay.
Yes, indeed.
And they said to us, Modicon, we like your product, but we need a method of handling this I/O remotely. All we want to do is we want to put some I/O boards 10 miles away and have this processor over here have access to it. Now, why don't you guys think about that? Because we'll buy thousands of them. Now, that got our attention. Okay. Voila, Modbus.
Right.
Nice.
Okay, remote I/O.
Wow. And it's nice to be able to hear what you're saying. And we're in 2025 and we've been dealing with this stuff for 40 years. And to have the introduction of the technology through your vision, knowing full well what's going to happen, it's fascinating.
It is.
Just fascinating.
Gary,
So I have one question though, and it's a little bit of a mystery to me, is that when you're inputting through the program panel, your 4 nodes and your output, how do you visualize it or do you visualize it in any way in the beginning?
I don't really understand what you mean.
Well, if we look at a piece of ladder logic now, we're looking at it on a string with, normally open, normally closed, and timers and so on and so forth. So as I'm inputting the node information, how do I keep track of what it was that I just did?
Well, the programming panel only allows you, or this is 084 programming panel now.
Mm-hmm.
Okay.
Yeah.
The 084 programming panel only allows you to look at one line. Okay. And you have a thumb turn switch and you dial up the line number. And then the system shows you the way it's programmed now.
Okay. Understood. I missed that part.
Okay.
Okay.
And that's it. Now, that leads to the problem of how do I document that?
Mm-hmm.
All right. So that's a whole other story. Okay. Because basically what we do is we take a memory dump, we bring it, and using the telephone lines, do a memory dump back to Andover. And then we have another piece of software that goes in and documents that, prints it out for you, and then we mail it off to you. Again, this is before electronic stuff and all this stuff. Everything's on paper.
Yep.
Okay. And by the way, we will not sell to you this magic electronic stuff that we have in Andover to extract that and print it out and mail it to you. We will not. That is our business. That is what proprietary software is all about. Okay. And we were big into that. Okay.
I mean, that would basically give you almost a source code. I mean, really.
Well, it gives you the source code of the ladder logic, which is fine because that belongs to you.
But the software that can take that memory dump and turn it into a beautiful printout, that I think would be too much IP to give away. That'd be almost giving away the farm, it would seem like.
Yeah.
Yeah. And that was chargeable, Chuck?
No, it was free.
Okay.
Okay. All we wanted to do, we were, King Gillette rides again. Okay.
Mm-hmm.
All right. You bought the razor. You brought the razor holder. We sold you the razors. Mm-hmm. Okay. In other words, you bought our product. We'll support the shit out of you. All right.
Mm-hmm.
Application advice, sure. No problem. We'll design the whole thing for you if you wish. All right. Just buy our product. That's all.
Mm-hmm.
That was it.
Wow.
Chuck,
Gary.
may I? So I do some teaching now at university to Gen Z students who I believe are
Gen Z.
20 years old. And that your term, we want to sell the shit out of this. I wonder if you have a Gen Z way of expressing that to my students who I'll meet 125 of them tomorrow in a business class. And I want them to sell the shit out of this pen. And that was just great. That was such a great, because that concept has not changed. We just want to sell the shit out of it. But I don't think you and Dick were on Instagram back in '68. Am I correct in that?
That's correct.
Oh my goodness. Okay. I would love to have a whole session on just Modbus protocol, because I fascinated you would say that, oh, well, we just came up with Modbus protocol. Well, guess what? It's, as you 2025, and going back at Triconics in the industry, a mere 25, 30 years, one of the first things I heard, maybe early mid-90s, oh, Modbus protocol, yeah, we're getting rid of that. We got this now. We got this new stuff. Modbus protocol, that's like way, way back. Guess what? It's 2025. Modbus protocol. So I just love the way you went over that like in a half a sentence, or what we just did Modbus. Amazing. We have to have you back, Chuck. So many questions. So amazed.
Yeah.
One more thing, and then so I have the title of your book. We'll just get AI to write it. So I called the Triconics Wonderware book "The History of a Safer World." I thought that was a modest enough title. Title of your book, Chuck, will be "The Beginning of Everything." Modest enough?
Yep.
The beginning of this. I actually believe that.
Because it really was. Okay. Let me just divert here just for a second, okay?
Mm-hmm.
Okay. We got the 084 kind of settled down. We're kind of in production. We made about 20, 30, 40 of them, okay? And we're getting pretty smug now, okay? And so we sit around one day and we say, what is the maximum number of outputs do you think anybody in their right mind would put on an 084? What do you think? What's the maximum? Okay. Because we can do 999 according to our numbering scheme.
Mm-hmm.
Okay. Divided by 16, whatever the modulo number is. Anyway.
Mm-hmm.
So, oh yeah, no problem. We got 999, no problem whatsoever. All right. 2 months later, in comes this salesman, Fred Henderson, one of the best salesmen we ever had. And he's got this little account called DuPont. You might have heard of him. Okay.
Mm-hmm.
And he comes in from Delaware, and this is not a phone call. He flies up to Andover, and he said, I got this problem that I have a customer, DuPont, that wants to use our machine, the 084, in a different way, but they have lots and lots of outputs. Mm-hmm. All right. Well, how many? 2,000 on one machine. And we look at each other. Oh, shit. Okay. Well, we have a problem. So that was the beginning of the 184.
History lesson continues.
Yeah, I'm looking at the time. We only have like 9 minutes left. Chuck, you've been awesome answering our questions. No, you've been awesome. I've so enjoyed learning this, and thank you for taking my questions. Jeremy, I know you had some more, and I don't know, Gary, if you have any more either, but I'll go to Jeremy first.
Well, Chuck, as expected, spellbound by your conversation. Would you agree to come back another time, maybe next week or the week after, for another hour, and we'll have
I got lots to talk about.
Okay. The one issue, and when I worked for Allen Bradley, and the PLC is what drew me to the company in the first place, and they said, "Oh, even though it's a computer, you can't call it that. You can't call it a computer." It was why the not? It's like, I mean, that's what it is. So, no, because people, and you have IT departments and so, and I know that Morley sort of coined that whole idea, and I know that you had something to do with that as well.
Mm-hmm.
So, how did that conversation go to say it's not a computer, it's a controller?
There are two parallel stories. Okay. One, computers in general at that time were unreliable as hell. I don't care who made them. Okay. And here's the important thing. They were not ready for the factory floor.
Right.
They were in glass houses, air conditioned, blah, 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 blah. Hundreds of minions would take care of them, blah, 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 blah. And the industry did not want that. They wanted their electricians to take care of this thing. We're just going to throw it out on the factory floor. We're going to overheat it, blah, blah, blah. All that good stuff. Okay, so reliability of computers at the time. Mm-hmm. Two, and this was interesting. Within this little company called General Motors, if you said in your purchase request, "I want to buy a computer," it would immediately go to IT. Of course, it wasn't called IT at the time.
No.
It would immediately go to IT. And of course, it would disappear into the firmament. Your request would just disappear. Okay. Mm-hmm. But if you said, "I want to buy a controller," oh, no problem at all. Here's the purchase order number. Fill it out. It's yours. All right. Just stay less than $2,000, and you can do anything you want.
Mm-hmm.
Okay. So there it is. All right. Now, Morley, the rule was, and it's still in my mind, still holds, the device was not called a computer. It was always called a controller. And the project name for this was stupid.
Yes, I read that.
Okay. Right. Because all the computers are.
Mm-hmm.
All right. They are the dumbest thing that walked the face of the earth.
All it takes is software.
It's just a small matter of software. That's all.
It's a small matter of software.
Chuck, by the way, I just looked you up in AI, and you made the cut. I misspelled your name at first, but I respelled it. It was not Chickshaw. So you've made it. How about that?
There you go.
Well, before you guys go, I just want to close out the show. I want to thank everybody who watched. We'll have a part 2 to this. And until next time, my friends, peace.
Peace.